Good evening, everyone. Today we shall study about power factor, which is there in the second module of your paper. We have studied power factor in the last year. It may be defined as the cosine of the angle of lead or lag between voltage and current in a circuit, or it is the ratio of resistance to impedance in a circuit. Then it is also defined as ratio of true power to apparent power. True power we know it is given by Vi cos phi. Apparent power is defined by Vi. So Vi cos phi divided by Vi will definitely give you cos phi. Then the true power is expressed in terms of watts and apparent power in terms of volt amperes. Hence, the power factor is also defined as watts divided by volt amperes. So these are the definitions for power factor. Now we have studied RL circuit, RC circuits, RLC circuits, etc. So we have considered RLC series circuits. We had studied only about series circuits in your last semester. In that we have seen the impedance triangle of an RL circuit. It was like this. The current in a series circuit, RL circuit is series RL circuit is constant. We are taking it as the reference. And resistance comes in phase with the current. Inductive reactance will be 90 degree ahead of that. And the resultant of resistance and reactance will give you impedance. This impedance will be at an angle phi. So as far as this impedance triangle is considered, the power factor cos phi is given by R by Z, resistance divided by impedance. This is called impedance triangle because the sides of the triangles are made up of ohmic values. So we are talking about power factor. Power factor is nothing but the cosine of this angle phi. Cos phi is equal to R by Z, resistance divided by impedance of the circuit. If we multiply all the sides by current, you will get the voltage triangle. And in a resistance, voltage across it is in phase with the current. VR, voltage across the resistance, that is given by current into resistance. That will be coming in phase with the current. So this IR phasor is in phase with current. And what about voltage across the inductor? In a pure inductor, current lags behind the voltage by 90 degree. So there is a 90 degree phase difference between voltage across the inductive reactance and current. So that will be exactly 90 degree. So the total applied voltage in this RL series circuit is given by vector sum or phasor sum of VR and VL, that is equal to V, that is given by I into Z. So this is the voltage triangle. Here also we are having phi. The total voltage in the circuit is given by capital V. Total current in the circuit is I. So, the cosine of the angle between total voltage and current is given by power factor. So, V by V, VR by V or R by Z again. Now, we shall consider the impedance triangle. By multiplying throughout by current again, the voltage triangle will become the power triangle. So this is the complete power triangle. The active power is represented by P, that is given by I squared R. The reactive power is given by I squared XL, represented as Q. And the apparent power or the total power is given by S, it is I squared Z. The angle is specified by phi between apparent power and active power. So cos phi is equal to P by S, active power divided by apparent power. I squared R divided by I squared Z or R by Z. So these are all definitions for power factor. Then if you are considering a capacitive circuit, RC circuit, the triangle will be downwards. The power triangle will be in the opposite or in the fourth quadrant. So the active power remains the same. Power is equal to I squared R. Phi is the angle here. So Vi cos phi will be active power. Q is the reactive power. I squared Xc. This will be 90° behind this power, active power. So Vi sin phi. Then apparent power is equal to I squared Z, root of P square plus Q square. Here also the power factor is given by P by S, Vi cos phi divided by Vi, or I squared R divided by I squared Z, or R by Z, or watts divided by volt amperes. All these are the definitions for power factor. Power factor is given by kilowatt divided by kVA, active power divided by apparent power. So from power triangle, power factor is given by Vi cos phi, active power divided by apparent power Vi, or apparent power square is equal to active power square plus reactive power square. Then what is the importance of power factor? Power factor plays an important role in AC circuits since the power consumed depends on power factor. We know that the active power is the actual power consumed. It is also referred as real power. Active power is given by Vi cos phi. From this you can find out the current. Current is equal to P by V cos phi in the case of single phase circuits, and if it is three phase, active power is given by root 3 Vi cos phi, or I is equal to total power divided by root 3 VL cos phi, where cos phi is the power factor. Here we can see for fixed power and voltage, if we are considering power and voltage as a constant, the load current is inversely proportional to power factor. That means as the power factor gets decreased, current increases. We know that power factor is given by cos phi and its value changes from 0 to 1. Minimum value of cos phi is 0 and maximum value of power factor is 1. So as the power factor becomes 0.5, the current will be doubled. So as the power factor is reduced, current increases. Current will be minimum only when cos phi is unity. Therefore, for low power factor means less than 1, higher will be the load current. Disadvantages of low power factor. As the power factor becomes low, the current will be increased so that the kVA rating of the equipment will be increased. For all electrical machines, the voltage rating will be fixed. So as the power factor gets reduced, the current will be greater. So kVA, if the current becomes greater, the kVA rating will become greater. As the kVA rating increases, the size of the equipment will be more and it will become costly as the current increases. As the current increases, the cross-section of the conductor being used inside the machine will get increased. Due to this, the total weight, size and cost of the equipment will get increased. Now, we have to use greater conductor size wherever the current flows. That is in the transmission line, transformers, equipments, all these may require greater conductor size in order to carry the increased value of current. Then large copper loss. Copper loss means I squared R loss. That is occurring on the conductor portion. Now, as the current gets increased, I squared R loss, which is proportional to square of the current, also will get increased. Then poor voltage regulation. As the current increases, I into R, drop in the resistance in the transmission line, in the machines will be increased. So, the regulation of the voltage will be poor. That means the sending end voltage will not get faithfully transmitted through the conductor and reach the consumer. At the consumer side, the voltage will be lesser due to IR drop. So the low power factor results in poor voltage regulation also. Causes of low power factor. The power factor is less than 0.8. It is normally referred as low power factor condition. The low power factor condition can occur both in inductive load as well as capacitive load. We know that in an inductive load, current is lagging behind the voltage by angle phi. In the case of capacitor, current is leading the voltage by certain angle. So according to this, the power factor cos phi also will get changed. We know that in an ideal capacitor as well as ideal inductor, phi is equal to 90. Angle between voltage and current is 90 degree and cos phi will be 0. In that case, the power consumed will be equal to 0. We know that in a pure inductor or capacitor, the power consumption is 0 because of this. But in a pure resistor, the angle is 0. That is, voltage and current are in phase. Due to that, phi will be equal to 0, cos 0 will be equal to 1. So maximum power is being consumed when the load is purely resistive. So lagging power factor as well as leading power factor results in low power factor condition. Most of the AC and induction type motors have LPL. We know that most of the loads in electrical systems are induction type. They are having lagging power factor and produces low power factor conditions. They work with very small power factor during no load, that is from 0.2 to 0.3 and rises to 0.8 to 0.9 at full load condition. Arc lamps, electric discharge lamps, heating furnaces, etc. operate at low power factor. Load variations in the power system also causes increase in magnetizing current and hence causes low power factor. These are the general causes for low power factor in power system. Then power factor improvement. Cause of low power factor is the presence of inductive load. Even though low power factor condition can be obtained due to the presence of inductive as well as capacitive loads, in the power system we are having inductive load mostly. Therefore, some devices stating leading power factor can be connected in parallel to improve the power factor of the load. So, inductive loads are producing lagging power factor, and if we are having some equipment having leading power factor in the same system, these two will get cancelled. Lagging effect will be compensated by leading effect and power factor can be improved. One such device can be a capacitor that produces power factor improvement. It can completely or partially eliminate the lagging effect. Consider an RL load. We can have a parallel RL combination like this in the diagram. The source is supplying a voltage E and let the current I1 be drawn by this RL load initially. Suppose the capacitor is not there, only RL load is there. Let the current I1 be drawn by the RL combination. Now, the total current I1 drawn is split into IL and IR through the inductor as well as resistor. This can be represented vectorially. The current IL and IR is shown here. Current through the resistance is in phase with the voltage. Current through the inductor lags behind by 90 degrees. So total current drawn from the supply is I1. It is the resultant of IL and IR. You can see that I1 has got this much value and lagging behind the voltage by phi1. Okay. Now this is producing low power factor due to greater angle phi1. In order to compensate this, as we have suggested, we can have a capacitor connected in parallel across this RL combination. Now the capacitor current comes in action and the total current drawn from the supply changes due to this additional current IC. Let the new value of current be I2. Now the currents IL, IC and IR can be drawn in the phasor diagram. You can see IC is a leading current with respect to the voltage. So it is 90 degree ahead of the voltage. IL is same as the previous case and IR is also the same. Their positions are also same. Now we can see IL and IC are in phase opposition. So the total reactive current will be resultant of IL and IC, that is IL minus IC. Since IL is having a greater value, IL minus IC will be downwards. Now the total current I2 drawn at this condition is given by resultant of IL and IC and IR. So IL minus IC is here, IR is here, resultant of these two is I2. Now due to the introduction of capacitance, we can see the current has been reduced. I1 is a greater value of current, I2 is a lesser value of current. Now the angle of lag is given by phi 2. It is also being reduced. So phi 1 was the initial angle without capacitor, without power factor compensation. Now due to the compensation of power factor by means of the introduction of capacitance, we can see that the angle has been reduced. So the power factor has been improved. So capacitor draws a current IC that leads the supply voltage by 90 degree. So that is represented vectorially here. The resulting current is the phasor sum of, that is I2. The total current drawn from the supply is the phasor sum of IR and difference between IL and IC. I1 is at phi 1 and I2 is at phi 2. Since phi 2 is less than phi 1, angle of lag has been reduced and the power factor has been improved. So by means of introducing the capacitor in a circuit, we can improve the power factor. So the following points may be noted from this. The circuit current I2 has been reduced compared to I1 after power factor correction. The active component remains the same before and after power factor correction. That is, the power drawn by the resistive component remains the same before and after power factor correction. So I1 cos phi 1 is equal to I2 cos phi 2 from the phasor diagram. That is, the real part remains the same or active component remains the same. For the resistive portion, the component remains the same. But the reactive component I2 sin phi 2 becomes equal to I1 sin phi 1 minus IC. So multiplying throughout both the sides by voltage, you can see VI1 cos phi 1 is equal to VI2 cos phi 2. Vi cos phi is the active power. So left hand side represents active power before power factor correction and right hand side represents active power after power factor correction. Both remains the same before and after power factor correction. So active power remains the same. But if we consider the reactive power, multiplying throughout by voltage, we will be getting Vi2 sin phi 2 is equal to Vi1 sin phi 1 minus Vic. Therefore, the net kVAR is the unit of reactive power. So the net kVAR after power factor correction, that is Vi2 sin phi 2 is equal to lagging kVAR before power factor correction, that is Vi1 sin phi 1 minus leading kVAR of the equipment. Leading kVAR is supplied by the capacitor, that is given by voltage into current in the capacitor. Okay. Correcting poor power factor can significantly reduce the load on the transformers and conductors. How? That is by reducing the current through them. Due to power factor improvement, the load current reduces. So loading on the transformer as well as the conductor system becomes lesser and allow for facility expansion. If the load current is reduced, additional loads can be added to the system. The low power factor typically results from unloaded or lightly loaded induction motors. Unloaded motor, the power factor will be 0.2 to 0.36. Loaded motor will be having rated power factor ranging from 0.8 to 0.9. Power factor improvement devices, examples are static capacitors. By introducing capacitors, we can improve the power factor. Then synchronous condensers, there is an overexcited synchronous motor in the no load condition can act as a power factor improvement device. Then phase advances. These are the three techniques for power factor improvement. Economics of power factor improvement. As power factor of the system is improved, the total current flow will be reduced, which permits additional loads to be added and served by the existing system. The load current will be reduced, so total load on the system will get reduced. So we can have additional loads. By improving power factor, current gets reduced and hence eliminate the overload condition of transformers, cables and generators. Maintaining high power factor in a facility will yield direct savings also. It reduced power factor penalties imposed by some utilities. In some of the suppliers, mainly in the private sector, will charge additional cost for low power factor conditions by observing one's power factor. Other savings such as decreased distribution losses, improved voltage regulation and increased facility current carrying capacity. The distribution losses will be reduced by reducing the I squared R loss by reducing the current. Improved voltage regulation is obtained by reducing the voltage drop. Voltage drop is I into R. If you reduce the current, I into R will get reduced. And increased facility current carrying capacity. If the load current is reduced, the facility will be capable of carrying more current. More efficient equipment performance, reduced carbon emissions. The equipment performance will be lesser, efficiency will be better if we are reducing the I squared R losses. Then reduced carbon emissions. If the efficiency is less, the power plant has to generate more. If the power plant generates more, in the case of thermal power plants, it will emit greenhouse gases like carbon that will affect the environment. So power factor correction affects all these generation as well as environmental pollution, all these issues. So with this, we shall stop this topic and we'll do some problems based on this in the next class. So thank you for listening.